guys, how are you doing? Okay, so what we discussed last time, remind me please.
Conductors that are display closed loop.
Okay, so some closed loop with electric current, which was uh, made from two conductors, one straight, another in the shape of a semicircle. And what we calculated there?
For the total force of the loop.
Okay, so we calculated the magnetic force exerted on the first conductor, then on the second. Initially, we determined the direction, like orientation of magnetic forces, where to be in opposite, like the same, uh, they were parallel to each other, but in opposite direction. And then when we calculated the magnitudes, regardless of the shape, since we had conductors of different shapes, regardless of the shape, um, the magnitudes of these magnetic forces were the same. So the same magnitude, opposite orientation. Eventually, we get zero as a sum of two vectors. So that means we can generalize this conclusion for all closed loops for um, um, cases when we have these closed loops with electric current in uniform magnetic field, that net force will be equal to zero. So we cannot move such a closed loop with electric current because of magnetic, since net force is equal to zero. However, I mentioned last time that it's not true for torque. And this is what we are going to discuss today, to quantify what torque will be exerted on a closed loop placed in a uniform magnetic field. And also, today we will discuss such an important effect called Hall effect, which allows to determine simultaneously mobility and concentration of charge carriers in different conductors. So let us start with the torque, and for that we will discuss such a case when we have a closed loop in the form of some rectangular so we can divide this loop in four pieces, so it will be 1, 2, 3, and 4. We will consider that electric current is floating counterclockwise. So we have the direction of electric current here, 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 and here. We place this closed loop in external magnetic field, which is oriented like this. This is our magnetic field vector. And now we need to consider which magnetic forces will be exerted on each of these segments, which are considered in the scope of the closed loop. So we remember that if magnetic field vector is parallel to the direction of electric current, so what do we have here? Segment 1, segment 3, they are parallel to the electric current direction is parallel to magnetic field vector. So in this case, the angle between them will be 0, sinus of 0 will be 0, and there will be no magnetic force. So we do not consider any forces exerted on these segments because they are absent due to orientation. So we still have number 2 and number 4 the segments, so we need to identify also the main like sizes of this. So let's say this will be the width will be b and the length will be a. So we can write that f1 is equal to f3, that's equal to 0. Then we have f 2 is equal to f4, and the magnitude of this magnetic field, magnetic force, will be electric current magnitude in the loop times A times B. Sorry, not this B, capital B. A times capital B. So we consider the length of the segment 2 and 4, that is 8, and magnitude of magnetic field vector B. So now let us consider this current loop from below. So we now will consider the projection of this current loop from this like bottom view. And let's show how it looks. So this is our side number 3, this lower one. So here at this edge, we will have electric current coming out from the plane of the image. And at this edge, electric current will go into the plane of the image. So this is this current through conductor 2. It goes down. So if we look from underneath, we see that it's coming out here. So, and this is current through segment 4. If you look from down, looks like the current is going in this point, perpendicular to the plane of our image. So if we consider some central point O, let us now define the orientation of magnetic forces exerted on this segment 2 and segment 4. So let me write that this is segment 2, this is segment 4. How we define the orientation? Who will remind me? Left-hand rule. So we have electric current now is coming out from here, and we need to align it so the vector, kinetic vector, goes into our palm. So that will be the orientation of magnetic force. So it will go up in this projection. So this is F2 vector. So similar we do for this opposite point. So current here goes into the plane. So we define that orientation of the magnetic force goes down. This will be F4 vector. Okay, so we have vectors, and now we want to determine what will be the torque which this forces exert on the current loop with respect to this point, central point O. So you see that obviously they are in a line in that way that they kind of tend to rotate the current loop about this axis which goes through point O. Here we have so-called shoulders. So this will be B over 2. And here's the same B over 2. Recall me how we determined the magnitude of torque? Tau?
I multiply icon with i's moment of inertia and the alpha is angular.
Well, that is when we consider already some kinematic parameters. But let's say we have force and force shoulder. So how we determine the torque? By the distance between the point where force is exerted and the point about which we kind of tend to rotate the system and want to determine the magnitude of torque. So in this case, we have the following. So it will be sum of two components. It will be F2 times B over 2 plus F4 plus, no, plus minus, multiply B over 2. Can factor out this B over 2 and consider it, let's say, like this, F. We know that F2 and F4 are equal to I times A times B. So let's write it for the force and factor it out. It will be I times A times magnetic field vector magnitude. And here we have B over 2 plus B over 2. So eventually we get I times A times B and times B capital. So what is this? A times B, that's area of the current loop. So we can go further and write that the torque will be equal to I times A times B. So we have magnitude of electric current in this closed loop. Then we have area of the closed loop A and magnitude of magnetic field B. So now we have the torque, and obviously we need to admit here that this will be the maximum torque because of the orientation of the current loop with respect to the magnetic field. If we, because of this effect of the torque, rotate the current loop at some angle theta, let's say, then the magnitude of the exerted torque on this loop will change. So let us consider this scenario. Let's assume that we have, that's our central point O, central point O, and let me let's say here So current orientation doesn't change, will be the same, but the orientation of this current loop is changed with respect to magnetic field, which stays in the same orientation. So now we will have, let me put this O here, and here will be some vector, which we call A vector. So A vector, this is such a vector which has the magnitude of the linear of the current loop. So it's A times B. And its orientation is defined by the right hand rule. So if we curl our fingers of the right hand in the direction of current in this loop, then the right hand thumb will show us the direction of this vector A vector. And we will introduce a little bit later the magnetic, another magnetic characteristic, and we will define its orientation in the same way. So it will coincide with the direction of vector A. So the system is tilted by some angle theta with respect to initial position. And here we have the same angle theta. So we have magnetic force F2 and F4. Their orientation stays the same because orientation of the current with respect to the magnetic field actually didn't change. They are also perpendicular, remain perpendicular to each other. However, we will have what actually changes, the shoulder of these forces is changing. So we need to write that in this case, the torque will be I times A times B. And here, instead of just B over 2, we need to multiply it by sinus theta plus B over 2 multiply sinus theta. And eventually we get I times A times B times magnetic field magnitude, and here we have sinus theta, which is I times area of the current loop times magnetic field vector magnitude times sinus theta. We see from this the expression for the magnitude of the torque that we can represent it in vector form as follows. So it will be torque will be equal to magnitude of electric current times cross product of A vector and B vector. So that is the general expression for torque, which is exerted on closed current loop in uniform magnetic field. So we need to take into account magnitudes of A and B vectors, their orientation with respect to each other, and obviously the magnitude of electric current which flows through this closed loop. So what we can introduce here is another parameter which I already mentioned, is so-called magnetic dipole. So if we consider some mu vector which is equal to magnitude of electric current times A vector, that will be magnetic dipole of the current loop. So it defined by the magnitude of electric currents flowing through the closed loop, its area and orientation, because it's a vector quantity of this current. So now when we introduce this magnetic dipole, we can express torque exerted on a closed loop in uniform magnetic field as magnetic dipole cross product with magnetic field. So that's quite simple form how we can express this torque. So if we have some torque exerted on a closed current loop in uniform magnetic field, that means we can use it for some practical application. So for instance, if we have some uniform magnetic field created by two poles of permanent magnet, and we have some closed loop with electric current flowing through it, we will manage to create some torque which tends to rotate this closed loop and transfer this torque to any other mechanism we want. So that's the basic principle of operation of all electrical actuators, motors. We just have many of these closed loops because there are many coils, and all of them experience this torque exerted on them because of permanent magnetic field around when electric current is flowing. So we use electric power to run current through this closed loop, and as a result, we get mechanical power of rotational motion. So we can transfer it and use another possible application, quite common, and there are still such devices. Most of devices are now digital, so they use different principles. But the most straightforward way to measure magnitude of electric current is to use amperemeter based on the this effect of exerting torque on closed loop in uniform magnetic field. So imagine that you want to measure current in some electric circuit. Let's say we attach this to some contacts. Here is our battery. Here is our resistor. And here is our current. So we want to measure magnitude of this electric current. And how we can do this? So we design such a system with permanent magnet and closed loop inside, fixed on some axis of rotation and fixed in position, like some left position, let's say, with some string. As we start to run electric current through the system, there will be torque exerted on this closed loop, and it will tend to rotate the closed loop inside this bag. Proportional, the torque will be proportional to the magnitude of electric current. Here is the equation. Means that if we calibrate displacement of this arrow proportional to electric current and torque which is exerted on this closed loop, we will manage to see on the calibrated uh, front panel of the instrument the magnitude of electric current floating through this electric circuit. So this is the operation principle of the electromagnetic ampermeter, which is one of the most straightforward way to measure magnitude of electric current. So let us now move to, why it doesn't? Let us now move to the Hall effect. So we know that the current density can be expressed in the following form. So current density J is equal to sigma times electric field magnitude. So this is which law is this? It's Ohm's law in differential form. And if we go further, we can write that this is equal to Q times N times mu times E, where sigma, from here we can write, this is specific electrical conductivity, is equal to elementary charge Q times concentration of these charge carriers and multiply by mobility. So we just considered an example how we can measure electric current. We use this torque exerted on a closed loop in external uniform magnetic field. We can calibrate this device according to the angle as much as closed loop will rotate when we reach balance between the exerted torque from magnetic field and exerted torque from the string. So they kind of compensate each other at each magnitude of electric current flowing through the circuit. And that will give us the magnitude of electric current. So we can measure this current density. Because we measure current, we know the area, cross-section area of the conductor. We have the current density. What about this electric field? We can measure it. Obviously, yes, we know the potential difference between two edges of the conductor. We know the length of the conductor. We divide potential difference by length. We get magnitude of electric field. Specific conductivity. So once we can measure J and know E, we get the specific conductivity. Sigma is equal to J over E. So no problems so far. However, we look at this equation, which gives us the expression of sigma, and see three parameters. So this is Q, we know that is like 1.6 10 to minus 19 coulomb. Well, for electron, if we consider minus, for positive charge. If we consider some hole in semiconductor, then it will be plus. And we have two parameters, n and mu, constant product of concentration of mobility and charge carrier concentration. So we want to know both. We want to know concentration of charge carriers, how many of charge carriers per unit volume we have in this conductor, and how fast they can move in this conductor upon some exerted electric force, because that gives us the mobility coefficient. However, if we know sigma, we cannot distinguish between these two guys to have a product. So we can get only product of concentration and mobility, and actual values of these parameters we cannot distinguish. So that is a problem, means that we cannot just measure current, like let's say current voltage characteristic, and get these two parameters. We need to use some other technique in order to deconvolute them and get the answer, like in numerical answer, quantitative number of each of these parameters. And the way how we do it, we employ the Hall effect. And that's very commonly used technique in field of electronics in general, and semiconductor physics, because this is a state-of-the-art technique which allows to determine both concentration and mobility with one measurement. So let us consider the basics of this effect, and we will have some conductor and some three-dimensional sample. We have X, Y, and Z directions. Let us assume that we have electric current flowing through this sample along axis X. And here we consider positive charge with some drift velocity vector in the direction of electric current flow. And let's say we have negative charge. In this case, drift velocity vector will be in opposite direction. So how we have two types of charges, positive and negative. So we consider, for instance, here semiconductor. Semiconductor may have both charge carriers. This will be electron, this will be hole. So it will be negatively charged and positively charged carriers. So that's what's going on when we just run current through this sample. Electrons are moving in opposite direction to axis X, also moving in along axis X. Now let us assume that we turn on the external magnetic field and assume that the orientation of magnetic field is along axis Y. So now let us see what happens. Obviously, there will be some magnetic force exerted on mobile charges. So this is positive charge. drift velocity vector, magnetic field comes into our form. So the orientation for magnetic force will be along axis z. Let's show it here. That will be magnetic force FB vector. Let's see what happens with this guy. So we have different orientation of the drift velocity, and we also need to consider the fact that we have negative electric charge. So eventually we get also magnetic force along axis z. So in both cases, there are magnetic forces exerted on these charge carriers. So now let us assume that we have just electrons. So it could be either metal or N-type semiconductor, which is doped semiconductor. When we have majority charge carriers electrons and minority holes, we don't care about that. So what will happen? Because of this magnetic force exerted on charge carriers, they will this magnetic force will deflect their trajectories and kind of push them closer to the upper side of the sample. So it will be kind of accumulation of negative charges at this edge of the sample. At the same time, since we have electrical neutrality, if we push this cloud of mobile electrons up to the upper edge of the sample, there should be some uncompensated positive charge at the bottom edge of the sample. So here we will get some positive charge. Maybe let me delete this, make it cleaner. So this will be some not compensated positive charge. What it means that we will create inside, because of all these processes, inside the sample, we will create internal electric field, so-called Hall electric field, which will be in the direction of axis z. So we used to have electric field driving force along axis x for running current through this sample. However, because of interactions of mobile charge carriers with magnetic field, we create this redistribution of charges, and there will be some potential difference between the top and bottom edges of the sample. So we consider between this and these edges. So this will be VH, so-called Hall voltage. And now if we add here the length and width of the sample, so this will be, let's say, A, this will be thickness T, and this will be D, the height of the sample. So electric field magnitude, which is along axis Z, will be now V whole divided by D. So that is the result of actually Hall effect, means the interaction of mobile charge carriers in a conductor or semiconductor with external electric field, external magnetic field, when magnetic field is perpendicular to the direction of electric current. In that case, we create potential difference between two different edges of the sample, and internal electric field perpendicular to external electric field, because again we have electric field along axis x initially, but now we create electric field perpendicularly to the external electric field. So until when this will happen? There should be some point when the process of accumulating these negative charges at the edge of the sample will stop. Any suggestions?
We're not considering the starting the current.
No, current is going.
Constant.
Yes, so this field is actually much stronger than this field, so it's just going. But what is the reason for accumulating this negative charge? Is this magnetic force, which pushes the charges close to the top edge of the cell. That means that it will continue until that building up this uncompensated negative charge at the top of the sample will continue until that time when magnetic force will be compensated by electrical force acting on these charges because of induced internal electric field. So in that case, we can write that at the steady state condition, QVD times B, which is magnetic force, will be equal to QEH. So they compensate each other, and then we get already steady state condition. Nothing is changing. We know that the current, or maybe let us express this the whole voltage. So delta VH, as I wrote, it will be EH times D, and that will be VD, oops, times B times D, because here we can cancel out this Q. So EH will be equal to VD times B, and if we want to get the potential difference, the whole voltage so-called, between top and bottom edge of this semiconductor sample, we need to multiply EH by VD, EH by D, so it will be VD times B times D. So now we have the expression for whole voltage, and let us express what will be the current. It will be Q times N times VD times A, where A is the area, the cross-section area of this conductor. And that will be Q times N VD times T times D. So T is this thickness and D is the height. So that is the area of the cross-section. From here, from this expression of electric current, we can express VD. And that is electric current divided by Q times N times A. Now we can substitute it here in the expression for whole voltage. So now we can write that whole voltage is equal to I times B times D over Q and A. So I, electric current divided by cross-section area of the conductor, that gives us the current density. So we can write here that J is equal to I over A. And we have here delta VH equal to J times BD over QN. So now let us make a substitution and introduce a new parameter which is Hall coefficient. RH is equal to plus minus 1 over Qn. Plus minus because it could be positive or negative charge. So we make this, introduce new parameter Hall coefficient, and we can express delta VH is equal to J times B times D and times RH. From here, we express RH, the Hall coefficient. And that will be plus minus J times B times D. Actually, it should be in the numerator here, delta V whole divided by J, B, and times D. So that is the expression for Hall coefficient. We know what is equal this guy. So it's equal to 1 over Q times. And look here at this right side of the equation. We have potential difference between the edges of the semiconductor. We can easily measure it. We have current density, which we also easily measure. We know magnetic field, and we definitely can measure the height of the sample, like distance between these two edges. So in the right side, we can measure all parameters, so we can determine this Hall coefficient. And the polarity, depending where is plus and where is minus, will give us plus or minus. So that will give us RH. And if we know RH, then we already, from this equation, can determine concentration of charge carriers. And that will be equal plus minus 1 over Q times RH. So that will give us the option to determine concentration of charge carriers. Once we know the concentration of charge carriers, we can come back to the previous equation. Sigma, we can measure it easily. It's J over E. And sigma is Q times N mu. Now we know sigma, we know N, and we easily get mu. So that's the way how we combine this effect of magnetic force on mobile charge carriers in a conductor in order to answer quite important question, how we get simultaneously in one experiment both values of concentration of charge carriers and mobility. So this is very useful technique, and those of you who are going to work with electronic materials, I'm sure you will definitely deal with this experimental technique. Thank you very much for attention. Have a good weekend and see you on Monday.